In this presentation, we'll examine how to write the equations of motion for systems consisting of two masses. The first case we'll examine are two masses m1 and m2 lying on a frictionless horizontal surface with a spring of stiffness K connecting them. An external force, F sub I, is acting on mass m2. This is the input to the system. The displacements of m1 and m2 from their starting positions, where spring K is at rest, are given by x1 and x2. Both these variables are indicated as positive to the right. If x2 minus x1 is greater than 0, then mass m2 has moved farther rightward than mass m1, and in this case the spring is elongated. If x2 minus x1 is less than 0, then x1 has moved farther to the right than x2, and the spring has contracted. So elongation is x2 minus x1, and contraction would be x1 minus x2. Of course, negative elongation is positive contraction. Let's develop the equations of motion for mass m1. And to do this, I'm going to conduct a thought experiment so that I can figure out how to write the relationship between the spring force and the motion of the masses. So here's my thought experiment. I'm going to hold mass m2 at its starting point. So x2 will be held to be 0. And then I'm going to make a positive displacement of x1. What happens in this case? In this case, the spring will be contracted. And that will yield a force on mass 1, which will push mass 1 to the left. Now we'll look at our free body diagram for mass m1. The displacement again is to the right, and that's labeled x1. And the only force acting on mass 1 is the force from the spring, which I label Fs1. I'm drawing the arrow to the right. This is the direction I consider to be a positive direction for the force. I could draw the arrow either way, but I've chosen to draw it this way, to the right, in the same direction as x1. Let's consider our thought experiment again. We said we're going to hold x2 to be fixed and move mass m1 to the right, so x1 would be positive. In this case, the spring is contracted, and we know that the force acting on m1 from the spring would be pushing m1 back to the left. So in this case, Fs1 would be negative. That tells us that Fs1 must be equal to negative K times the contraction. The contraction was positive in this thought experiment. Fs1 must be negative if it's drawn to the right, and therefore the relationship has to be Fs1 equals minus K times the contraction. Since the contraction was x1 minus x2, we have the equation Fs1 equals minus K times the quantity x1 minus x2. So now we found the relationship between the two displacements, x1 and x2, and the spring force on mass 1. From the free body diagram, we can write the equation of motion for mass 1. It will be m1 x1 double dot equals the sum of the forces acting on mass 1, which is the spring force, Fs1. Note I wrote m1 x double dot equals Fs1. That's because Fs1, as shown in the free body diagram, points to the right, which is the same direction as positive x1. So Fs1, if it was positive, would result in positive acceleration. Now, substituting in for Fs1 our equation, Fs1 equals minus k times x1 minus x2, I find the equation of motion m1 x1 double dot equals minus k times the quantity x1 minus x2. Let's now develop the equation of motion for mass m2. To do this, we'll conduct another thought experiment. In this one, we'll hold x1 at 0, so mass m1 is not going to move, and we'll make a positive displacement of mass m2, so x2 is positive. This will result in the spring being elongated. And when the spring is elongated, it will pull on mass m2 back to the left. Here is the free body diagram for mass m2. Positive displacement x2 is to the right, and we have the external force, F sub I, the input, acting to the right as well. Now, of course, this just indicates that this is the positive direction for the variable F sub I. We don't really know which direction F sub I is acting in. It could sometimes be acting to the right and sometimes to the left. I've also drawn the spring force Fs2 to the right. Of course, the spring force could be to the right or to the left as well. But when I draw the arrow and label it, I mean that this is the direction that is the positive direction for the spring force. In the thought experiment, I said that I was going to hold x1 constant and move x2 to the right. And in this case, the spring elongated. And under elongation, the spring will be pulling back on mass m2 to the left. So with elongation, I know Fs2 will be negative. That tells me the relationship between Fs2 and the displacements x1 and x2. I know that Fs2 will be equal to minus k times the elongation, because when x2 is positive, the elongation is positive, and Fs2 will be negative. So for mass m2, I know that Fs2 will be equal to minus k times the elongation. Furthermore, I know the elongation is x2 minus x1, and therefore I know Fs2 is equal to minus k times x2 minus x1. I'm now ready to write my equation of motion for mass m2, and it will be m2 x2 double dot equals sum of the forces acting on m2. In this case, I've got Fs2 and Fi acting in the positive x2 direction. So the equation is m2 x2 double dot equals Fs2 plus Fi. And I know Fs2 is minus k times x2 minus x1. So I can substitute that in, and I find the equation of motion m2 x2 double dot equals minus k times the quantity x2 minus x1 plus Fi. Summarizing these results, my equations of motion for the two masses are: for mass m1, it is m1 x1 double dot equals minus k times the quantity x1 minus x2. And for mass m2, it is m2 x2 double dot equals minus k times the quantity x2 minus x1 plus the input force Fi. Now we'll find the transfer functions. We'll assume zero initial conditions, and we'll Laplace transform these two equations. That yields m1 s squared x1 of s plus k times x1 of s equals k times x2 of s, and m2 s squared x2 of s plus k x2 of s equals k x1 of s plus fi of s. Now I've done a little algebra to rearrange terms. I've pulled all the x1s to the left-hand side in the first equation and put the x2s on the right-hand side. In the second equation, I've pulled all the x2s to the left-hand side and put x1 and the input force on the right-hand side. To find the transfer function, I need to know what the output is. This system has two masses. The displacement of either one could be the output of interest to us. So we'll need to specify which one of the two masses displacements is our output. And for this example, I'm going to suppose it's x2. So the output, y of t, is equal to x2 of t. And of course, if I Laplace transform that, I find y of s is x2 of s. So now I'm going to find the transfer function between the input force Fi and the output y. That is, from the input force to the motion of mass m2. Now to find this transfer function, what I'm going to need to do is eliminate the variable x1 of s. I've got two equations and three unknowns. I'm going to use one of the equations to eliminate the unknown x1 of s, leaving a relationship between x2 of s and fi of s. And that relationship will be our transfer function. So we have our two equations of motion now in the frequency domain, and we're going to do some algebra. We're going to solve equation number 1 for x1 of s, and then we're going to plug that into equation number 2 to eliminate the variable x1 of s. Then we'll do algebra to bring all the x2 of s terms together, and then divide through to find x2 of s in terms of fi of s. And that will yield the transfer function. We find x1 of s is equal to k divided by m1 s squared plus k times x2 of s. And this is what we substitute into equation number 2 for x1 of s. That yields an equation after we collect the x2 of s terms as m2s squared plus k minus k squared over m1 s squared plus k all times x2 of s equals fi of s. You can see one of the benefits of working in the frequency domain here. We're able to do algebra on differential equations. That's because the Laplace transform transforms differential equations into algebraic equations. The equations are now algebraic, but nevertheless the algebra will be tedious. So here's a page with quite a bit of algebra. And what we're doing here is trying to get everything that's inside the curly brackets over a common denominator, and then simplify the numerator. And once we've done that, we can then divide through by the term in the curly brackets to bring it onto the right-hand side. And when we do, we'll find the following. The transfer function between input force Fi and output displacement x2 is m1 s squared plus k divided by m1 m2 s to the fourth plus k times quantity m1 plus m2 s squared. This is the transfer function between Fi and x2 and is labeled g2. Since x2 is the output of the system y, this is the same transfer function between Fi and y. Now here I've written it slightly differently. I've done a little algebra to clean it up, and I've defined a quantity me, which is sort of an equivalent mass, and it's m1 times m2 over m1 plus m2. And you'll find this term in the denominator. With this defined, the poles of this fourth order system are the roots of the denominator polynomial. These are clearly 0, 0, minus j times the square root of k over me and plus j times the square root of k over me. The square root of k over me is the natural frequency of vibration of the two-mass system. We label it omega n. The zeros of this system are as follows: minus j square root of k over m1 and plus j square root of k over m1. So this transfer function has two poles at the origin and a pair of complex conjugate poles at omega n on the imaginary axis. The modes associated with these poles are e to the 0t, te to the 0t, e to the minus j omega nt, and e to the plus j omega nt. The first two of these correspond to translation of both masses together. The second two correspond to a vibration of the masses at a frequency of omega n. In the complex plane, the poles will show up on the imaginary axis, and these are marked by an x. They're at plus and minus j omega n. The zeros are marked by an O. They're also on the imaginary axis, and they're at plus and minus j omega naught. There's also two poles at the origin, and these are what are referred to as the rigid body poles. The poles on the imaginary axis at plus and minus j omega n are the poles associated with the flexible modes, that is, the modes of vibration of the two masses moving toward each other and then away from each other. So we've now found the transfer function between the input Fi and the displacement of mass 2, and we've called this transfer function G2, and we found its poles and zeros. In our next lecture, we'll examine the transfer function between the input Fi and the displacement of mass 1,